Okay, we're going to get started with Chapter 6, the Datum chapter in our GD&T class. This is a very important chapter because datums are going to be used throughout all of the geometric tolerancing that we're going to do from this point forward. The only type of GD&T tolerance that does not use datums is, as you just saw, the form tolerances. So this is an important topic. We're going to divide this up into two sections. So there'll be a part 1 and a part 2 here. All right, and then I will also do a video of some worksheet problems, some application problems, so that you can kind of see how that is done. I think that's important because the lectures will only get you so far, but really seeing how the ideas and concepts are applied are going to be vital. So anyway, so let's get started with Chapter 6, Part 1, Datums and Datum References. All right, so first of all, why do we need datums, or what are datums? What's the point of a datum? Well, geometric tolerances may be used to define relationships between features. Okay, so remember, features can be a surface, a hole, a cylinder, a groove, anything like that. We're talking about features or features of size. Okay, so remember that there's two different ways that we can look at that. But geometric tolerances can often be used to define relationships, like that surface is parallel to another surface, or that cylinder is perpendicular to this surface, or those two holes are located relative to the edge by some dimension. Okay, so these these tolerances that express a relationship between features include orientation tolerances, positional tolerances, profile tolerances, and some of the other ones as well. Okay, these tolerances therefore must have datum references. Datum references are what links a feature that we're trying to control with another feature, with the geometric relationship between another feature. Okay, so that's how we express that with datums. A datum feature reference indicates which datum features establish the theoretical datums from which measurements are made. Datums define, and I want you to remember this statement because this will really get you through a lot, okay? Datums define where the part lives in the assembly, okay? Where the part lives in the assembly. All right, that's important, and we'll revisit that later, probably in section 2 or part 2 here. So, datum feature references in a feature control frame can be found on the back end, on the right side, right? So in the front, on the left side of the feature control frame, we have the tolerance symbol, and then we have the tolerance value, and then after the tolerance value, we have the datum references. Okay. And these are letters shown in the feature control frame to the right of everything else, right? They're called out in individual boxes. These are our datum references, okay? The first datum reference, the one farthest to the left, right, just adjacent to the tolerance value, is always the primary datum. And that carries more importance. That carries the most importance in terms of datums, okay? So A, in this case, is the primary datum. The second datum after the primary datum is called the secondary datum, all right? And then the third datum is called the tertiary datum, all right? So these are always in order: primary, secondary, tertiary. It has nothing to do with the letters in the alphabet, okay? This could be X, M, and A, right? The first datum here is always the primary, second is the tertiary, second is the secondary, third is the tertiary, okay? Now, we're allowed to have material condition modifiers in with our datums, all right? And we'll talk about that, but it's the same as our material condition modifiers with our tolerance, okay? So now it doesn't have to be. Notice that here we can have a material condition modifier with this positional reference, positional tolerance, but that doesn't mean that we have to have a circle M here. All right, here we have a circle M and a circle M in the secondary. Okay, so that's just according to the part specifications or the design intent. All right, so this is a little bit more terminology. Okay, some of this is important to know. All right, some of it, you just want to keep in the back of your mind while you're reading. It'll come up. But on a drawing, here's our datum feature symbol, right? And it's kind of like a little flag, right? We have a base of the flag, and it's typically a black triangle that's filled in. It could also be a triangle that's open, but I think in this book they use the black solid filled triangle. And then the datum reference, in this case, this is datum A, right? Notice that it's hanging off of the extension line, okay? That identifies this surface on a drawing as the datum feature. So this right here, this surface right here is datum feature A, all right? Now what that means on the actual part is this, all right? So the actual part is symbolized here with rough contours, right? Because no part is going to be perfectly smooth like that. So we have rough contours. The datum feature is going to be this actual surface, right? The actual bumpy surface. Well, we can't really use a bumpy surface as a datum because a datum needs to be a theoretically perfectly flat plane. So we use a theoretical datum plane A that the part is going to rest on. And notice it rests right there and right there and right there. So it's sitting stably on theoretical datum plane A. So datum plane A is that dashed line. Datum feature A is the actual part. Datum feature A on the drawing is the actual surface of the object on the drawing. All right, doing a little bit more. All right, let's continue with this fabricated part, the actual part, right? This is the drawing. This is the actual part when we make it. So here we have right here, this is called the theoretical datum plane A is also called the true geometric counterpart. What that basically means is that this is how we simulate the datum plane because the actual surface is an imperfect surface. Okay. Now, when we put the part on a table to measure it, right? Because that's what you're going to do. You're going to measure the parts to make sure that they are follow according to the dimensions and geometry that we specified in the drawing. We're going to put it on a surface, right? And we call that the tool. So let's call that the tool surface here. Now that surface is also going to be imperfect, right? It's less imperfect. These are very, very highly precise and accurate surfaces, but it's still not a perfect surface. That's impossible to make. So we're also going to have a simulated datum plane A, right? So the actual datum, the tool surface is called the Datum Simulator, right? And the theoretical datum plane for the Datum Simulator is the simulated datum plane A. So when we put the two together, right, and that's what this is showing, right? Here the two are apart. So imagine now that we take the part and we place it down on the surface. What we end up getting is kind of a part that nestles in there. It sits on top of, and it may rest in some of the valleys, some of the shallow valleys on the tool. And we have the theoretical datum plane A with the simulated datum plane A, and theoretically they should lie right together, but of course, they're not going to, because of the imperfections in the fabricated part and the tool. All right. So what this means is that we have to be able to deal with simulated datums and theoretical datums. Okay, because in real life we have parts that are imperfect. We have nothing. No surface is going to be a perfectly flat surface. All right, so we have simulated datums, and notice the simulated datum on this fabricated part is derived from these 1, 2, 3, 4 data points. Right, now where we get those data points is from measuring the surface with a coordinate measurement machine or some other device that we use to measure the surface. And that's from that surface, we're going to be able to develop the simulated datum, right? So it's going to be, the datum is going to be a surface going through those 4 points. The theoretical datum is going to hit all the high points of that surface. All right, so there may be a little bit difference between those two. So again, to recap, the datum feature is the physical feature on the part. Datums may be surfaces or features of size. The datum is the theoretically perfect point, line, or plane on a drawing. Okay? So the datum feature is the actual feature on the part, the physical part. The datum is the theoretical perfect point, line, or plane on a drawing, right? So this is my datum A, right? And this is my datum feature A, the imperfect surface. The true geometric counterpart is the theoretically perfect counterpart of the datum, right? What do I mean by counterpart of the datum? Well, here's the datum. The datum is the surface from the drawing. And so the true geometric counterpart is the theoretically perfect counterpart of the datum that we would find. Okay, the datum simulator is the tool that we use, the physical tool used to provide a surface or axis, plane, or point from which measurements are made. Okay, now all that being said, it's good terminology to know. Don't get hung up on this. If this is kind of like making your brain feel like mush right now, just put it to the side. Just remember datum, all right? Just remember datum, maybe datum features, all right? But we don't have much more to do with this until later on, so it's not like a huge big deal, all right? So don't get stuck on this. So let's talk about the datum reference frame. This is important, all right? The datum feature references in the feature control frame establish a datum reference frame. So these 3 letters, or it may be 2 letters, or it may be 1 letter, whatever, all right? These letters over here, these datum feature references, establish a datum reference frame. So in this example right here, this A primary, B secondary, C tertiary datum references create the ABC datum reference frame. All right, the ABC datum reference frame. So A, B, and C, the datum reference frame is always made up of 3 mutually perpendicular planes. So think of it as like the corner of a room or something, right? So we have the floor, datum plane A. We have the wall back here, datum plane B, and then we have the wall perpendicular to that, datum plane C. So these are 3 mutually perpendicular planes, all right? Now, the datum reference frame always has to be made up of 3 mutually perpendicular planes. You can't have two perpendicular planes and 1 plane that's parallel to one of the other. No, that doesn't work. All right, you can't have 3 parallel planes. You have to have 3 mutually perpendicular planes. We're talking about in what you should notice here is what we're really identifying is 3 planes in space, right? So we have, let's think of this as the XYZ axis, right? So we have datum plane A, we might call that the XY plane. Datum plane B, we might call that the XZ plane. And datum plane C, we might call that the YZ plane, right? So those locate the three axes that form the X, Y, and Z coordinate system. Okay? So remember, these letters in the feature control frame define a datum reference frame. In this case, the datum reference frame that we're looking at is the ABC datum reference frame. All right? Datum reference frames are chosen based on functional requirements of the part. Remember that phrase, where does the part live? How does the part move? Those two questions are how we determine what our datum reference frame is going to be. Now, multiple datum reference frames can and do exist on single parts. Why? Because parts go into assemblies, and individual parts interface with multiple other parts. They have a lot of different neighbors. Okay? So let's look at an example here. All right. So in this case, we have I don't know. This actually was taken from a drawing for a spacecraft, for a NASA spacecraft. Okay. So we have some type of body here. We have a hole in the body, in the center of the body, right? And we have an O-ring that goes inside that groove in the center of the body right there, around the hole. And then we have a cover that's going to go on top of the body, and it's going to be screwed in. So we have 3 screws, 1, 2, 3 right there that go into those tapped holes, right? Now, what you can't see is on the other side of the cover is a little cylinder that goes into that hole. All right. So this assembles like this. The seal, the O-ring, goes into the groove, and the cover goes on top of the body and is screwed down. And then we have a key that is screwed onto the side. And notice this little notch, this little tab in the key is going to fit right in that notch on the cover, so that the cover only can go one way. The cover can only be assembled one way. All right? So very simple assembly, right? Cover, seal, body with a key. So let's look at a drawing. How would we define a drawing and the datum reference frame for the cover? Okay? So what we want to do is we want to ask ourselves, where does the part live? Where does the cover live? And I think if we go back to the drawing, it's clear to say the cover lives on the surface of the body right here, right? So that's this red line right there. All right, so that surface is an important surface. It's where the cover sits on the body. The cylinder that you can't see here, the cylinder, goes into the hole. So the cylinder is also an important feature when we ask ourselves, where does the part live, right? So the part lives, the surface goes onto the surface of the body, the cylinder goes into the hole in the body, and finally, the key goes into this groove or notch in the cover, right? And I've identified all these surfaces as red, right? So that's where the part lives, right? That's the unique location where the part lives, right? Now, you might ask, well, why didn't I call out the holes? You know, why the part seems to live with the holes? Well, not really. If you think about it, these holes right here are going to be clearance holes. So there's not any contact necessarily between the bolt and the cover hole, right? There is contact between the cover surface and the body surface. The cylinder here, there may or may not be contact, but it seems like it's important for the cylinder to go into that hole. That helps to locate it, right? If the cylinder doesn't go in the hole, then the cover ain't on there, right? And then finally, to get the rotation of the cover correct, we need the key to fit into this notch. All right. So those are the 3 areas where our part lives, where the cover lives. So how does that play in the drawing? Okay, so we're going to call this surface, right, the base of the cover, the flat surface of the cover, we're going to call that datum A, right? And we're going to call the cylinder datum B, right? Now, it just so happens that datum A is a datum surface, right? It's just the surface. Datum B, because we're calling out a cylinder is a feature of size, so we need to call out datum plane, or datum B, datum feature of size B, in a special way, which we've done here by hanging it off of the size dimension for the cylinder. And finally, datum C, well, this is also a feature of size, right? Two opposing planes with a size dimension create a feature of size. It's just like a rectangular hole, right? And so datum feature of size C also needs to be associated with the size dimension. All right. So now what do we do with this information? A, B, and C. Well, we need to identify which datum is going to be primary, which is secondary, and which is tertiary. And we have to go again back to our design. In this case, we definitely want the cover to sit flat on the body, right? That's our primary concern. We don't want any gaps to exist, right? And so that primary concern corresponds to a primary datum, right? And we can see that here, here, and here. All right. Now, we also want the secondary datum to be this cylinder, right? Because that's also important. We want the cylinder to go into the hole straight. And so that becomes our secondary datum. And that's what we call out here. Secondary datum. Now, it just so happens that that is datum feature of size B, maximum material boundary. We'll talk about what that M, circle M, means. All right. But then our tertiary datum, the third one in order, is C. And again, that also gets a maximum material boundary datum, material modifier, circle M. So what that means is the part lives, and if we look at this, how many datum reference frames do we have on this part? Well, each one of these combinations is a unique datum reference frame. So we have A, that's datum reference frame. That's a datum reference frame. We could call that datum reference frame A. Then we have ABM. That is the second datum reference frame, ABM. And then we have a third datum reference frame, ABMCM. So we actually have 3 datum reference frames on this one simple drawing of one simple part. A, ABM, and ABMCM. Now, if we had some other, feature control frame in here, I don't know, maybe there was another special hole in here, and that hole was also ABMCM, that's not going to make a 4th datum reference frame because it's the same as this. So a datum reference frame is always called out for each unique set of datum references in a feature control frame. In this case, we have A, ABM, and ABMCM, 3 datum reference frames in this part. All right. Here's another example of datum reference frames. Now, this is a little bit of an older drawing, so you see an S right there. That S has been removed from the standard, and now the S stands for regardless of feature size, and now we don't need that S to indicate regardless of feature size. But here, how many datum reference frames do we have in this drawing? Well, we have A, we have AB. I'm going to ignore the S because that's not it's RMB, regardless of material boundary. So AB. So we have A, AB, and ABCM. So we have 3 datum reference frames for this drawing, for this part. What does this mean when we're trying to simulate the datum reference frame for this part? All right. Well, what that means is that the part is going to, and here we're going to focus on ABCM. All right. ABCM is the one we're going to focus on. So what that means is that we're going to identify datum plane A, right? Remember, primary is A, all right? And that's a datum plane. So we're going to simulate it with a flat surface. All right, here's A right there, that flat surface right there. Where's B? B is this hole, right? B is that hole. And it's regardless of material boundary, right? So B right here is regardless of material boundary. And what is datum B? Datum B is that hole, right? So datum B is called out as the hole. There's datum B right there. We actually identify it as a datum axis, right? Because a hole is going to have an axis, just like a cylinder does. And what is C? C is this slot right there. So that's datum feature of size C. And C, we're going, in the ABCM datum reference frame, C is at maximum material boundary. So there's our datum plane C, right? This identifies a datum plane. Right, datum feature of size. Just like this datum feature of size B for a hole identifies an axis, datum feature of size C for a slot identifies a datum plane, right? And so there's our shape right there. Now, you can imagine this on a measuring surface, right? We have a flat table. We put a cylinder down at a specific location. All right, are those given here? Yeah. Well, I think some of them are kind of left off here, but there would be basic dimensions locating that. All right, they've just left that off here. And then we have this rectangle that's going to go into position where the slot is. All right, so this would be on our measuring table, and then how we measure the part is we need to place it around these features. And so there it goes. So we put the part around these features, and then we can measure it. So these features locate a datum reference frame. These are 3 mutually perpendicular planes. Now you might be wondering, well, the axis isn't really a plane. Well, yes, but it establishes it allows us to establish a mutually perpendicular plane from A and B. B is a plane, A is a plane, and so C would be that last plane perpendicular to both of that. Or excuse me, B would be that last plane perpendicular to A and C. All right, going through the axis. And so there we go. So the part has to sit down in that. This is where the part rests when we're doing our measurements to verify our geometric controls and tolerances. All right, that's what that is. So that's what the datum reference frame is. That's what datums are. They give us kind of the basis, the ground from which we're going to measure the tolerances on our part. All right. All right. So let's look at this a little bit more about the datum reference frame and talking about degrees of freedom. All right. So in space, in 3-dimensional space, we have 3 translational and 3 rotational degrees of freedom. All right. So if you take an object, maybe a stapler in your hand, maybe a calculator in your hand, anything, a phone in your hand. Hey, you know what? You got a phone, right? So if you're holding your phone in your hand, all right, you can move it in 3 directions, right? Holding it in your hand. I wish you could see mine, but holding it in your hand, you can move it to the left and to the right. That's one direction. You can move it up and down. That's two directions. And you can move it away from you and towards you. That's three directions. Those are our three translational directions. Okay? Now we have three rotational directions. So take your phone with you, and now I want you to rotate it around the vertical axis, right? That's one rotational degree of freedom. Then we can rotate it around the horizontal axis. That's two rotational degrees of freedom. And then we can spin it so that it rotates like a clock. And that's our third rotational degree of freedom. All right? Datums constrain the degrees of freedom for a part. They lock it down in space. Let's go back to this part right here. Can this part move? No. Can we take the part and slide it in either the X, Y, or Z direction? No. Right? We can't slide it around down the X-axis, right? Because the datum feature C and datum feature B prevent us from doing that. Same with the Y-axis. We can't slide it on the Y-axis. Now, you might be thinking, well, wait a second. We could just pull it up, right? We could slide it around the Z-axis. No, we can't, because the part has to remain in contact with A at all times. So, and now, can we spin it? Can we spin it around the Z-axis? Well, clearly no. The datum feature C prevents us from spinning it around the Z-axis. Can we spin it around the X-axis? Well, no. Datum plane A prevents that. Same with spinning it around the Y-axis. All right, so this part is locked down in space. It cannot move. Once we put it onto this datum reference frame, then it's locked down in space. All right, the part may not be completely immobilized though. Okay, rotation and translation may be permitted based on part function. So if we go back to this part right here, all right, so let's say we didn't have this key. All right, let's say we didn't have the key, and it really didn't matter the orientation of the cover, right? You could put it on this way, or you could rotate it 60 degrees and attach it, or you could rotate it another 60 degrees and attach it. It really didn't matter. What mattered is that the cover sits on the base of the body, and that the cylinder of the cover goes into the hole in the body. So in that case, we wouldn't need C, and this would be ABM, right? Now, is the part going to be locked in space? Well, it's going to sit on datum feature A, datum plane A. It's going to line up the axes with datum axis B. But then it's going to have 1 degree of freedom left. What degree of freedom is that? Well, it's going to be able to rotate. Now, why would we allow it to rotate like that as it's resting on A and it's aligned with B? Well, because that's the part function. The part function is allowed to rotate. All right. All right, so let's look at how we identify datum features on a drawing. Now, you've already seen that in some of the drawings, right? We use a square or a rectangle connected by a short line to a triangle. Typically, we have one letter in the square identifying the datum features. In some cases, we can have 2 letters, but let's not worry about that right now. They're only applied to actual features. You never put this on a center line or center plane on a drawing, right? Never do that. All right, so when we're identifying datum features, right, datum surfaces, whatever, datum features, we can rest the datum on the actual feature, or we can put the datum on a extension line, okay? Now here, we want to remember, we must clearly separate from the dimension line, right? There's the dimension line right there. Putting this little triangle over the dimension line, opposite the arrow, means something entirely different. So you got to keep that away from the arrow when you're talking about datum features. All right. Now, when you're talking about datum features of size, okay, now we need to associate the triangle with the arrow, just like it is here, or just like it is here. This one looks a little bit weird, but this is still legal, right? It's associated with the dimension line. Remember, that's your dimension line. This is your dimension line. Here, not associated with the dimension line, because here we're talking about a feature, right? Not a feature of size. All right. When we use a datum to call out a feature of size, whether it's if it's a cylindrical feature of size, then we're really identifying a datum axis, right? A datum axis. When we use the datum for a rectangular feature of size, we're really calling out a center plane. All right, some more datum identification. These are all datum features of size, right? So remember, datum features of size, we have to associate the datum plane with the dimension line. So here, dimension line attached to the triangle. So that's datum feature of size A. Again, same thing here. Here, dimension line, yes, so that's good. Here, now notice there's not really any room to do that. So what we do is we hang it off of the leader, which is still identifying as a datum feature of size. And of course, we can also identify it by hanging it off of the feature control frame. Whether it is a datum feature of size, in this case, the feature control frame will be associated with the size dimension. Or if, let me go back a couple ones here. To datum A, let's go here. Yeah. Here we have a datum feature A, right, which is a non-size feature. This is not a feature of size. This is just a plane. And we've hung that under the feature control frame. All right. So it is critical. It's very important that you understand the correct way to apply the datum symbols on a drawing. All right, because that's a big deal, right? Putting it on the wrong way means something completely different. All right. And that's where we're going to stop. All right. So that concludes part 1. We'll pick up part 2 with slide number 24.